All right. I wanted to show solving one of those limit at infinity problems with a double fraction because sometimes they're a little confusing. Um, I'll also introduce you to a different way to think about them if you like plain polynomials better. Uh, and I'll also teach you how to interchange the two kinds of problems. But let's analyze this as they gave it to us. For now, I'll uh, I'll unscribble this eventually, but for now, as x approaches negative infinity is what we'll do second. We're going to focus on x approaches infinity, right? And then the logic might work or not because sometimes things change when you've got a negative sign. Sometimes they don't. So the first thing to realize about the cool thing that's going on here, even with an ugly double fraction, and I'll use green. That -5 does not change no matter what x is. And the same with that +6. The -5 and the 6 remain fixed. They don't vary with x. I'll just pause for a second. They don't change. So the question becomes, as x approaches infinity, do the other terms kind of disappear into minor error and we're left with -5/6? Or do the other terms get really big in a way that's unpredictable enough that we can't get an answer? Or do they get really big in a way that is predictable so we can find an answer? We have to figure it out. So let's do it numerically, right? One of the best ways to deal with these problems to sort of get a computational feel for them is to use tables of values and, pull out your calculator to do it, or, do the arithmetic by hand with some approximation going on. Um, the goal there is by doing some computations with these kinds of limits at infinity problems, you'll get familiar with what the algebra always does, no matter the exact values you use. So you'll be able to sort of dynamically think about, oh, okay, I know as x gets bigger and bigger, this happens to that part and that happens to the other part. And you can kind of think in dynamic algebra as opposed to using a fixed set of numbers that get bigger and bigger. But we start with that. Nothing wrong with starting with straight computation. So if we want to approach infinity, then probably it's a good idea to, start with some big values. I don't really know what big means, but let's try 10, right? Um, and then let's do 100, and then 1,000, right? And so on. The numbers I can see, -5, 7, 6, 4, they seem, I don't know, small enough that 10 and 100 and 1,000 shouldn't bump into them badly. What I mean by bump into them badly is, getting something undefined. And if I really want to worry about that, all I have here is like, if x is 0, I know I have undefined stuff. And I know that if the whole bottom was 0, I'd get undefined also. But I don't really have to worry about exact spots the function goes bad, because my job is to figure out what is the trend as x gets bigger and bigger and bigger. So I'm just going to do this. Probably I'll skip all the way to 1,000,000 as soon as I figure out those three, because I can probably see the pattern. And then I put infinity here, but it's really approaching infinity. You can't plug in infinity as a number, but we'll see a trend, or we won't see a trend. If there's a trend, then we'll answer with the end of the trend. This is all arithmetic then, right? You plug in 10, look at this, -5 plus 7/10. That's the top. And the bottom of the fraction, that's 6 minus 4/100ths. Now, you know, since you've got a calculator in front of you, you could have used any numbers you want. I used powers of 10 because I noticed, oh yeah, that'll give me decimal approximations pretty easily. So when I use my calculator, what I want to do is actually show it to you in 2 steps. You'll see why in a moment. When I take -5 and add 7/10, I get -4.3. And when I take 6, positive 6, and I subtract 4/100ths, I get 5.96. Okay? That's pretty close. 5.96 is close to 6. Not, there's only a 4% error. Close to 6 there. This is not very close to anything in particular. So when I use my calculator, right, I'm not actually going to punch it in. I'm just going to tell you it's right. So just allow me to go, it's approximately, right? It's approximately -0.7. Right? I'll put a little scribble afterwards to sort of, maybe it's lower than -0.7, maybe it's -6.9, and that would have rounded to 0.7, right? I'm estimating. You can just jam that into your calculator, get the answer, boom, there you are. Next, let's see what's going on. The -5 stays the same, but now when we use 100, it's +7 over 100. Huh. Hundredths is a lot smaller than units. Why don't we convert the top right now while it's on our mind? -5 plus 7/100ths, -4.93. That's quite close to -5. Now what about the bottom? 6 minus 4 over, well, now it's 100 squared, so that's that's 2 zeros plus 2 more zeros, 100 times 100. Yikes, 10,000. So, wow. I mean, look at this. This bottom of the fraction is very, very close to 6. It's a little bit smaller because we subtracted something very small, 5 point. Hopefully I have the right number of nines. Tenths, hundredths, thousandths, 100,000ths. I believe that's the answer. This one is very, very close to 6. Very close to 6. This one is reasonably close to -5, right? It's a little smaller than -5. The bottom is a little, sorry, the top is a little bigger than -5. The bottom is a little smaller than 6. So we're going to get something close to -5/6. Not quite there. The top is closer to 0. The bottom is also closer to 0. Again, if you use your calculator, I'd make a bet it's -0.8 something. Let's skip 1,000. Let's go right to 1,000,000. And let's just kind of skip right to over here, right? That's 7 millionths above -5. -4.10ths, hundredths, thousandths, 10,000ths, 100,000ths, millions. Look how tiny, look how very, very close to -5 we are. And this one, it's 1,000,000 squared. That's one with 12 zeros after it. That's billions. I'm going to use a ... pretty soon, but right, plus, right? It's positive 5.999 9. All right, I'll be annoying. I'll write out all 11 of the 9s. Oh, I'm getting bored already. 11 of the 9s, and then there's like what? We've lost 4, so there's a 6 at the end, right? This is really, really close to -5 over 6. That's the actual algebra with a little bit of faked up arithmetic. Please do it on your calculator if you need to see the actual numbers at the end. Um, you'd have to kind of recognize that -0.8333333 repeating would match -5.6. On a multiple choice, you could probably reverse engineer that. It's kind of unfortunate that you get decimal answers all the time if you're using a calculator. But here's the point. You really don't need to use your calculator if you realize, hey, they set it up so I could think about it conceptually. I'm going to circle this in red, right? They set it up so that the x approaches infinity was underneath a number. They set it up so that it was clear 7 over x, as x gets bigger and bigger and bigger, gets smaller and smaller and smaller. So that term right there shrinks to nearly nothing as we take the limit as x approaches infinity. And the same thing goes on here. This x squared gets larger even faster, right? See how fast? All those 9s, more 9s, and again, a 9 there, really close to 6 even at the beginning. So this one, that little term, constant divided by a bigger and bigger and bigger number, that goes to 0 even faster than the top one. We don't really care how fast they go to 0, we just care that they each go to 0. So go to 0. They turn into very, very small values as x grows large, which really means that the top is very, very close to -5. The bottom is very, 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 very close to 6. So as x grows larger, the answer gets closer and closer, right? In other words, we could have just, at the green phase, we could have realized, oh, x getting bigger and bigger makes that drop out to 0, and that drop out to 0. And the final answer is just -5 over -6, right? So now you can dynamically think about algebra. You didn't need to do the table. You just needed to realize that if you plug numbers in conceptually without knowing the exact numbers, you know that that 7 over x term shrinks smaller and smaller, and that -4 over x squared term shrinks smaller and smaller. So in the overall computation, double fraction or not, they don't matter. Something near very near -5 over something very near 6 is -5.6. There you are. That is the beautiful, quick way to solve it. Don't focus on the double fraction. Focus on the fact that, hey, this is written in such a way that as x grows big, that term gets tiny. And if both terms get tiny and I've got stuff left over, then they just turn into minuscule errors. And the errors will keep shrinking, so the answer is -5.6. Now, I do want to show you a variation on this one item. What if, and I'm just saying what if, they're not always going to show it to you. What if instead of this, I'll cross it off in red. What if instead of this, right? What if instead of this, they started you out with just a plain old polynomial, right? What if it was -5 x squared plus 7x on the top, and it was 6x squared minus 4 on the bottom. Polynomial over a polynomial. We'll take a look at that polynomial over a polynomial, and let's apply the idea of dynamic algebra. Let's not do computations, but let's do thinking. So immediately, 10? I don't know if I like 10. Let's try something bigger. Let's do 100. Let's think about 100. When you square 100, you get 10,000. So this top is negative 50,000. Oh, but then we have 7x. Remember, 7x is 700. Negative 50,000, but we're adding 700. 700 is not very big compared to 50,000, right? 50,000, 700 isn't even 1,000. So you're only off of negative 50,000 by, less than 1/50th. 50,000, you're off by 700, less than 1 out of 50 error. Let's look at the bottom when we use 100. 6x squared is 60,000. Oh, but we have the minus 4, right? We got to deal with the minus 4. Wait a second. 60,000 compared to the number 4? I mean, forget the 6 and the 4, right? That's some number of 10,000s versus a few units, right? That's somewhere in the range of, some number of units per 10,000. That's a very small error. Even if it was like kind of big, maybe it would be maybe round up to 1 error in 6,000, right? And we could say the same thing for the one on the top. Maybe the 7 compared to the x being 100, right? We said 1 error in 50. Maybe it's a little bit higher. 500. Maybe it's not, right? They're sort of negative 50,000 on the top, sort of 60,000 on the bottom. So the answer is sort of negative 5 over 6 with some errors. But now I'd like you to think about x being 1,000. Remember, 1,000 squared is 1,000,000. So the top is negative 5 million. Let me do this for emphasis. Negative 5 million, right? And then the second term is plus, it's just 7,000. Look at that. What's the amount of error there, right? 5 million versus 7,000. Let's forget about the 5 and the 7. Let's just say some millions and some thousands. Thousands are a tiny portion of 1,000,000. Thousands are only like, 1,000th of 1,000,000. So the error here can be measured. The error is on the order of, I'm off by 1,000th. And when we look at the bottom of the fraction, oh goodness, that's negative 6 million. Again, we're using x as 1,000. And then minus 4. Oh my goodness. Again, let's kind of blur our eyes at the 6 and the 4, right? Kind of like we kind of ignored the 5 and the 7 and just go, if they were roughly the same number of millions versus units, well, the error, again, the error, well, this is units against millionths. So the error is around 1/1,000,000th. Basically, what we've got here is the top is no more than 1 out of 1,000 away from negative 5 million. And the bottom is no more than 1 out of a million away from 6 million. So basically, we're looking at negative 5 million over 6 million with a tiny bit of error, smaller error than when we thought about putting in 100. That's the point. Those errors keep shrinking in proportion to the big number, the bigger the x we put in. Some people really like saying that to themselves. The highest degree in a polynomial is the only one that matters when we have infinite limits. Negative infinity counts too. It's the only one that matters if we have two polynomials. Just the highest term. This one just shrinks to error, and right, anything of lower degree, that's counted in x's, that's counted in x squared. What happens if you plug in a billion? Well, that's 7 billion, which seems big, but over here is 5 with 18 zeros after it. Billion, trillion, quadrillion, quintillion. Negative 5 quintillion is nearly a billion times larger than 7 billion. So the error keeps shrinking. And the same thing here, except it's even worse. That's error, and those errors, because as x grows larger, the errors shrink. Those errors essentially shrink to insignificance compared to the large terms. And then after we see that, we go, oh, the large terms can cancel out. It was 5 million over 6 million, 5 billion over 6 billion, 5 quadrillion over 6 quadrillion, and teeny, teeny, tiny errors to the side. So you can see that the x squared and the x squared are almost exactly, they're exactly the same. And the final answer is off by that tiny little error. It's the same thing as the green approach, right? Look at what they did. They made the negative 5 show up, and they made the 6 show up. All they did to the original was they divided by that highest degree that they saw anywhere. They divided by the highest degree that they saw anywhere. They divided every single term equally by x squared. That's the only way you can get away with dividing by something in any kind of fraction or expression, right? Divide the top by x squared, that means both terms get divided by x squared. Divide the bottom by x squared, that means both terms get divided by x squared. And look what happens when we simplify. X squared over x squared cancels, and we get negative 5. X over x squared, well, the x cancels out the power 2, leaving us with x to the first. That's right, that's plus 7 over x. And the 6x squared over x squared, oh, that cancels out to 1, right? That goes to 1. That goes to 1. 6 times 1 is 6, so we write it down. And what's 4 over x squared? Well, that's just negative 4 over x squared, right? Algebraically, this and that are identical. Just division by x squared of every term. Some people like to look at this and go, I quickly see when x gets big, that term goes to 0. And when x gets big, that term gets to 0. So only the negative 5 and the 6 are left over. You can do the same thing, whether it's polynomial over polynomial or this kind of constant with fractions shrinking to 0 and constant with fractions sinking to 0. Only the constants matter here, because these matching degree terms were equal. One more thing to add to the lesson. What if we have a big polynomial, right? And then I'm just going to scribble x squared and lower stuff. right? What if we have a big polynomial and over here we have a small one? I'll put x squared plus stuff, right? Remember, the straight polynomial way, you just look at the highest degree term. Oh, let's use 5 and 7 again. Throw the 5 there, throw the 7 there. That's what we're allowed to do. We can just toss out everything, right? When we have limit as x goes to infinity. Sorry. Let's always comment on that. So let's think about it. All of these terms, x squared and lower, shrink to near nothingness when you make x large, because everything is x squared or lower, and this is x cubed, right? Plug in 1,000, you got 5 billion. And then you got things in millions and thousands, right? Millions and thousands are nearly nothing compared to billions. And then try x is a million, right? Oh my gosh, x cubed, a million cubed, that's x with, what is it? 18 zeros after it. Yikes. I think that was quadrillions. Oh, the rest of it shrinks to zero, right? This stuff shrinks to zero compared to the first term. And the same exact reasoning down here. This stuff shrinks to zero compared to the first term. So this is approximately 5x squared, sorry, 5x cubed over 7x squared. But then you go, oh, x is not zero, x is a positive number, and x cubed cancels with x squared. So you get 5x over 7. You can think of this, I'll just rewrite it a little bit. It's 5/7 of x, but x is going to infinity. 5/7 of x? Well, I mean, you take 5/7 of infinity, you get infinity. Doesn't matter what you multiply, what number you multiply infinity by, you still get infinity. There are some exceptions to the rule, like 0, you don't get anything computable, but this is just a little scaling of infinity. Well, you're scaling something infinitely far away, you stay infinitely far away. So you can say, right, they told us we're allowed to say, right, plus infinity, right? If we had the plus infinity coming in, we're allowed to say plus infinity to indicate this is growing without bound. That's what it does. As x grows, grows without bound. Okay, one more. Still a limit as x goes to infinity. Pick your favorite number. I'll make it 21. This is going to be your x squared, and there's going to be leftover stuff, right? And 3x cubed. 3 is another favorite number of mine. My birthday is March 21st, 321, so I usually pick them if I can because they're my favorite numbers, right? You happen to have, oh, let's make it more complicated. Not really, right? This one's x to the fourth, right? Doesn't matter, that just means everything else. It's the same deal, right? As we take the limit as x goes to infinity, everything that's x and lower shrinks to zero, shrinks to minor error in comparison to x cubed. And everything here, third degree and lower, shrinks to zero in comparison to the x to the fourth. We've talked about that a lot, right? So we have minor errors differing from the answer of 21x squared over 3x to the fourth. All right, but that equals, right? That equals 21 over 3 is 7, right? That equals 7. Wait, 7 over x squared, right? We could cancel x squared with x to the fourth and get x squared left over. Just for a little clarity, let me just write that as 7 times 1 over x squared, just to really emphasize what's going on. Well, remember, we know that 1 over x squared goes to 0 as x goes to infinity, right? The larger and larger x becomes, the smaller and smaller the fraction 1 over that bigger and bigger number becomes. So you get 7 times 0. right? Or at least something approximating 0, right? And then when you take the actual limit, you go, oh yeah, that shrinks down to 0, and the limit is 0. So 7 times 0 is 0. I said the right thing. I wrote the wrong one. 0. Why 0? Because look at the original problem. The bottom polynomial is so much bigger that it dominates the top one. It gets huge compared to the top one. So you get a number divided by a number that is increasingly huger and huger. 1 divided by bigger and bigger, that goes to 0. And the top one, opposite. The top grows faster than the bottom does. So when you cancel, right, the top goes faster than the bottom does. So the ratio gets larger and larger and larger. That's like saying the limit is plus infinity. This is how we think about x goes to infinity. I didn't mention negative infinity, but all you'll find is sometimes you're off by a negative sign. Like on this page over here, x cubed. If you had a negative sign, that would go to negative infinity. The bottom would still go to um, positive infinity. So when you cancel out, you'd have a negative and a positive. So you'd go to negative infinity. Um, the bottom example, they're both even powers. So the negative infinity squared or to the fourth power, the negative cancels. So there's just a little bit of carrying negatives into exponents to worry about. Not a whole lot to worry about in terms of plus versus minus. So don't be too concerned um, about what's going on with the x values. It'll all work out in the end.